let's do the slower version. Oh, yeah, I'm in the wrong folder. So let's matrix dimension master agree. Which line is that? 23. Which dimension wouldn't agree? So okay, so let me make a breakpoint and run this. FIL is what? 1 by 2? Oh, UL. Oh, I need this. That's one of the mistakes. So let's run it again to make sure there is no other errors. Okay, yeah, maybe let me plug in my power. Second. So in this, so at the very end, okay, dwdt. Okay, so I have one more. Then, oh, here is the problem, right? Okay. So this is again forgetting the second dimension. So now it works. So let's try it. Try it that way. We're going to run the code again. Do you have these oscillations appearing? So let me just make sure it is a shock capturing problem, just by allocating a much higher dimensional, make it a larger grid. And if we do that, we make a larger grid. Should we? Unable to meet. Sorry? Oh yeah, that's right. So let me see. Thanks. That's also incorrect because now I have to say when I plot it, I have to plot it to length of u0 divided by 2, right? does seems to be a shock capturing problem. Can you say again in the diffusion term, which is here?
Yeah, so in the end, what was the problem? It have to be 1 over delta x. So d times delta
Right. Oh yes. Right. Oh, okay. Yeah, that's a good point. I think this delta x shouldn't be here because yeah, in the let's see, in the numerical dissipation, yes, this actually would cancel. So here actually shouldn't be a delta x. It should be 1, right? Because the otherwise, when you plug this into a finite volume scheme, this delta x would get cancelled. We still want a diffusion term that is proportional to delta x. So thanks for that. Yeah. So okay. So I was adding too little numerical dissipation into this into the scheme. So okay. Let's see what I did last year. Is that what the problem is? Oh yeah, I added a new interface of the delta divided by delta x. That's the difference between this year's code and last year's code. Okay, thanks. So okay, so that's a mistake I had, and let's try it again. So from where? From the initial condition, I set u0, and loop over. Wrong folder again. So now we see that kind of the water sloshing around the back and forth in this domain, right? So initially we had a sinusoidal height with no velocity, and as the solution evolves, basically it initially develops several waves, but everything finally collapses into a single wave that just sloshes around back and forth. So let's actually maybe slow down a little bit since we spent so much time making this code work. And thanks for finally giving the right debugging information to make it work. So let's see. Pause 0.5. This. I think I plotted the wrong thing again. Why does it always go to here? So where is the pause by 0.5 and this is correct. So this is the initial waves developing, and so what you can see is that on the shallower water, which is the lower value of the solution, the waves actually run slower, and that's because the wave speed is u0 plus square root of hg, right? For lower g, both waves are closer to the actual velocity of the water. So basically the higher water column is actually going to catch up with the waves on the lower water, and the waves collapse onto each other to form a single shock wave. And this is basically similar phenomenon as you see on beaches, where like a higher water column, which is the tip of the wave, collapse onto lower water columns. So this is kind of the physics described by the shallow water equation.